Every time you look up a question, stream a video, or load a web page, somewhere a server is working for you. And that work generates heat, a lot of it. A large data center can consume over 100 megawatts of electricity, enough to power a small city. Most of that energy ends up as waste heat, blown into the atmosphere by cooling systems that exist for one purpose: getting rid of it. But what if that waste heat wasn't waste at all? To answer that question, we need to talk about a working fluid that behaves unlike anything in a conventional power plant: supercritical carbon dioxide. There are two classical ways engineers turn heat into work: the Rankine cycle, which moves a fluid through liquid and vapor phases, and the Brayton cycle, which compresses and expands a gas continuously. The key difference between them comes down to compression. On a pressure versus volume diagram, the shaft work required to compress a fluid is the integral of V dP, the area swept between the compression path and the pressure axis. Let's look at the area for each cycle. Liquid-specific volume is roughly 2 orders of magnitude smaller than gas-specific volume at comparable pressures. The difference shows up directly in the work integral, and directly in the back work ratio, the fraction of turbine output consumed just by compression. In a gas turbine, up to 80% of what the turbine produces goes straight back into driving the compressor. And that is the work the cycle generates but never delivers. So the question becomes, is there a fluid you can compress almost like a liquid but still expand through a turbine like a gas? Every pure substance has a critical point, a specific temperature and pressure beyond which the distinction between liquid and vapor ceases to exist. To understand what that means, let's build a phase diagram from scratch. At low temperatures and high pressures, the substance is a solid. As we cross this boundary, the substance melts into liquid. The liquid-vapor boundary is the saturation curve, followed upward as pressure and temperature both rise, and it terminates. That termination is the critical point. Below it, heating a liquid at constant pressure eventually causes it to boil, which is a sudden, discontinuous jump from liquid to vapor. Properties like density, specific volume, and enthalpy change abruptly at that boundary. Above the critical point, that discontinuous jump never happens. But the significance is not just the absence of a phase boundary. It is that you can move continuously from a liquid-like state to a gas-like state, with no abrupt change in properties at all. Density, specific volume, enthalpy all change smoothly. There is no boiling, no condensation, no sudden transition. Just a single fluid whose properties shift continuously with temperature and pressure. Now here is what makes CO2 special. The location of the critical point is a fixed property of each substance, and it varies enormously. For water, the critical point sits at 374 degrees Celsius and 22 megapascals. Conditions so extreme, they demand specialized materials throughout the entire system. For CO2, the critical point is at just 31 degrees Celsius and 7.4 megapascals. That's just above room temperature at a pressure that is high but industrially achievable. Watch what happens when CO2 is brought to its critical point in a sealed tube. The boundary between liquid and vapor, that sharp meniscus, simply vanishes. What remains is a single, uniform fluid that is simultaneously dense like a liquid and expandable like a gas. This is supercritical CO2, and that dual nature raises a precise question. What does it actually cost to compress a fluid in that state? For an open flowing system like a compressor, the work per unit of mass is the integral of VdP between the inlet and exit pressures. That integral is the area swept between the compression path and the pressure axis. So what matters is the size of V, the specific volume during compression. Bigger specific volume means bigger area, means more work in. Look at the isotherm right at the critical point. Near that inflection, the slope approaches zero. The curve goes nearly flat. That means a large rise in the pressure produces almost no change in specific volume. The fluid is so dense at that condition that it behaves far more like a liquid than a gas, and compressing a liquid costs a fraction of the work. Let's zoom in on that region and put some real numbers to it. Note that this diagram flips the axes, with the pressure along the bottom and specific volume up the side on a log scale. We are looking right at the neighborhood of the critical point, from 70 to 160 bar. The 31.5 degrees Celsius isotherm, just above CO2's critical temperature, traces along the bottom. At that condition, specific volume is roughly 0.0015 cubic meters per kilogram. The green region beneath it is the compression work, the unavoidable baseline. Now look at the red region stacked above it. That is the additional work penalty at just 41.5 degrees, only 10 degrees warmer. At that condition, specific volume has climbed to around 0.004 cubic meters per kilogram, nearly 3 times larger. Since compression work is the integral of VDP, 3 times the specific volume means roughly 3 times the work. Staying closer to that lower isotherm is exactly what the cycle is designed to do, and the payoff shows up directly in how much the turbine's output you actually get to keep. We've seen why supercritical CO2 compression costs less on the PV diagram. Now let's see what that means for the full cycle on the temperature versus enthalpy diagram, because this is where the full cycle consequences show up. For a standard air Brayton cycle, the isobars fan apart significantly on the TS diagram. That fanning reflects how much enthalpy rises during compression in a gas. At backwork ratios of 40 to 80%, a large fraction of turbine output goes straight back into driving the compressor. The net work, the enclosed area, is what remains, and it works out roughly to 55% of turbine output once you account for real-world component losses. Now look at the supercritical CO2 cycle on the same axes. Near the compressor inlet, right at the critical point, the isobars are pinched tightly together. That compression is the near flat region we saw on the PV diagram, now showing up here as a short, shallow rise in enthalpy. The backwork ratios drop roughly to 25%, and the net work fraction climbs to around 75%. The turbine output is comparable, the heat input is comparable. What changed is that compression term. Same 4-process cycle topology as Brayton, same basic thermodynamic structure, but by operating CO2 near its critical point, the cycle keeps far more of what the turbine generates. The difference comes entirely from where on the phase diagram the compression happens. There is one more modification that real supercritical cycles always include, and it compounds the efficiency gain significantly. It is the same principle as regeneration in a gas turbine. In a supercritical CO2 cycle, the turbine exhaust exits at a high temperature, too valuable to simply discard. So before that heat is rejected, it preheats the compressed CO2 on its way to the heat source. That internal heat exchanger is called the recuperator. The external heat input drops because part of the energy is recycled within the cycle itself. In a well-designed supercritical CO2 system, the recuperator can recover a large fraction of that turbine exhaust energy, pushing projected thermal efficiencies above 50%, competitive with or exceeding the best supercritical steam plants. So where does this actually go? Start with what has already been built. In San Antonio, the STEP demo facility completed phase 1 testing in 2024. The turbine ran at 27,000 RPM, reached 5,000 degrees Celsius, and delivered 4 megawatts net to the grid. That turbine produces the equivalent of roughly 21,000 horsepower and weighs under 100 kilograms. Anyone used to steam plant scales would not recognize it. While the US was validating the technology, China moved to commercial deployment. In December 2025, the world's first commercial supercritical CO2 power plant connected to the grid. Named Nguyen, 2 15-megawatt units at a steel plant in Guizhou province, running entirely on sintering exhaust that would otherwise be lost. Compared to the steam recovery system it replaced, it delivers over 85% higher generation efficiency and more than 50% greater net output, which brings us back to where we started. Whether a compact supercritical cycle can turn industrial waste heat into grid power is no longer an open question. The temperatures here are lower and that engineering work is ongoing, but the thermodynamics transfer. Those numbers on the chart are not about better materials or more advanced combustion. They're about compression and where on the phase diagram it happens. That is the answer to the question from the opening. But CO2 got here because its critical point happened to sit at an accessible temperature and pressure. Other fluids have critical points too, which makes you wonder, what else is sitting on that phase diagram, waiting for the right cycle to be built around it?